Okay.
Okay, so I'm just gonna briefly recap the standard secretary problem first. So in this problem, we have a set of n elements. And by the way, so my handwriting is not the best, but I mean, I will try to write things as legibly as possible. But if you can't, it's not clear what I've written, let me know and I'll kind of fix that. So I have a set of n elements. And these are like, you can think of them as basically, you can think of them as numbers in the real line. You don't really have to, you just need the comparison operator. But let's say n elements, for now, let's just think of them as numbers that are like W1, W2, and Wn. These are real numbers. And these numbers are arriving in random order. And my goal is to maximize, and like, so when these items arrive, at any point I can decide whether or not I accept the current element that I'm seeing, right? So I don't know these numbers up front. So let's say, it's like 1, 3, 5, 0, 2, right? These are going to arrive in some random order. So let's say I see 5 first, then I see 0, then I see 3. And at any point, so when I see the current number, I can decide whether or not I accept that number or not. If I accept the number, then that's my number. If not, I'm going to go to the next number and, I can't come back. So decisions are irrevocable.
This is essentially secretary problem, but here this is the version that actually we have the value for the items and not just comparing more than that.
Yeah, so the decisions are irrevocable, and yeah, for now we can just assume like the simplest version, which is I just want to maximize the probability of accepting the maximum element. So in this case, really, whether or not I think of these as numbers or not, it wouldn't be important. If I want to, so like there are two notions I can consider. Notion one is maximize probability that, let's say W star is accepted, where W star refers to the maximum element. The second notion I can consider is maximize expectation of accepted element. And just to clarify, I can only accept one element. I mean, the notions are kind of closely related, but like there are like for technical purposes, like the difference between them can actually be somewhat subtle. For instance, for proving lower bounds, considering the first notion, I think is like much easier than the second notion. It's just much harder to prove lower bounds against that. But it's kind of clear that the first notion is intuitively stronger in the sense that if let's say I have an algorithm that let's say for some algorithm I have the probability of W star is accepted is P star, sorry, is let's say P, then that would imply that expectation of accepted element is bigger or equal to P times W star. So if I have an algorithm satisfying the first notion, it also has guarantees for the second notion. I'm now going to discuss a very simple algorithm that'll achieve a probability of 1 over E for accepting the optimal element. So I'm just going to focus on the first notion, and I'm going to show that you can actually achieve the acceptance probability of 1 over E. And in a way, you can think of this, if you kind of ignore constants, then this is basically like, this is actually quite a good thing, right? So it's like, even if I have a million or a trillion elements, I can still ensure that the maximum element is chosen with probability 1 over E, which is like 0.3. It's not that low, right? It's higher than 0.3, but yeah. Yeah, so I'm not going to discuss the algorithm. Are there any questions so far?
Any questions?
Okay. So what is the algorithm going to do? So I'm going to assume that n is large, by the way. You can assume this because, I mean, this is like some of these assumptions, like without loss of generality, to just simplify the math. You can always assume that n is very large because, well, if I have an algorithm that works for n equals 1,000,000, and I want to solve the problem for n equals 10, then I can always create a new instance where I just add a bunch of add a bunch of elements with weight 0. I won't kind of go to the details of that, but like intuitively, yeah. So there's a reduction you can do.
So n is the number of elements that are coming, and also we are assuming random order here, correct?
Yeah, exactly.
So we are assuming that these numbers essentially are coming in a random order. You can think about some unknown distributions that these are coming there. That would be a random order. But these are numbers that they can come anyhow. Somebody has done it. They have just essentially permuted randomly and then give it to us.
Yeah, exactly. And the main reason I'm going to assume this is just to simplify the math. So like, notions like, for instance, floor of n over e versus, ceil of n over e. I don't want to kind of, get down to those details because like it'll just get things messy. So I'll just kind of, approximate all of these with n over e, right? And if n is large, you can see why that's kind of, these numbers are going to be huge. So like the relative difference is going to be very, now you can easily ignore that. So now, what is the algorithm going to be? Algorithm is observe the, let S be the first n over e elements, right? So I have n elements arriving in random order. I'm gonna chop off the first n over e of those. So like roughly 36% of them. So when the elements in S arrive, I'm not gonna accept them. These are just gonna be my samples. So I'm gonna completely ignore this. For I in let's say we can just use the floor notation for simplicity, but like n over e n. So let ei be the element time I if w of ei, and by w of ei I just mean the weight of ei, is bigger or equal to the maximum of s. So like just think of it as a maximum weight in s. Then accept ei. So basically, I take like a sample of the elements, like roughly 36% of them, and I record the maximum number there. And after that, I accept the first element that exceeds this maximum number. So that's the algorithm. Let me know if there are questions. Otherwise, I can just like kind of go straight to the proof of why this chooses the maximum element with probably 1 over e. I know this was already covered. I'm just recapping the algorithm for
Yeah, we talked about the algorithm, but here not the analysis.
Yeah. So yeah, so what is the like proof that this works? Well, let E star denote the maximum element. So I want to prove that probability of E star is chosen is bigger or equal to 1 over E, right? How do I show this? Well, fix some time index, fix I in the range n over E plus 1 all the way to n, right? Denote, yeah, so I can write, let's see, let me just, basically the main point is that in order for E star to be accepted, it needs to be accepted at some time step between I, n over E and n. And therefore the probability of it being accepted, I can just write this as the sum of it being accepted at those times. So probability E star is chosen equals sum n over E, I is in n over E to n, probability E star is chosen at time I, right?
Because before that it is 0.
Yeah, before that it can be accepted, and all of these events are disjoint. So I can just sum the probabilities to get the probabilities on the right hand side. Now, how do I lower bound each of these terms, right? So in order for E star to be chosen at time I, first of all, I need to arrive at time I, right? So I have a 1 over n probability that arrives at time I. This is because, the order is uniformly random, right? Secondly, now once this happens, then it's already going to satisfy, the second condition here that is going to so if you look at our algorithm, the condition I had is that the weight of the element needs to be larger than the maximum weight of the samples. So it's going to satisfy that. However, the problem is that I'm not necessarily guaranteed to have the ability to accept E star because I might have accepted an element earlier. So as long as I reach time I, E star is at time I, and I have not accepted an element, then I would accept E star, right? But the problem is I cannot necessarily guarantee that I have not accepted an element. So what I need to do is I just need to lower bound the probability that I have not accepted an element, and that would immediately kind of lead to a bound on the probability of me accepting E star. So probability of, just to kind of recap, so E star is chosen at time I is, I'm just gonna write bigger equal to for simplicity, but probability that E star is, arrives at time I times probability that no element is accepted before I. So this probability is just the first probability is just 1 over n. I'm not going to just discuss the second probability. So if I think of these elements, right? So they're arriving in some random order. So this is the first element. This is the second element. Let's say this is time I. And let's say this is the sample set S, right? Then time I. Then as long as, so if I look at the elements before E star, then if I look at the maximum element there, I claim that as long as the maximum element appears in the sample set, then no element will be accepted before E star, right? And this is kind of easy to see because if I take all of these elements and the maximum of them appears in the sample, then any element that appears after the sample is not going to satisfy the condition that I have here. So its weight will not exceed the weight of the samples, the weight of the maximum of the sample. Therefore, it will not be accepted. So when I reach time I, E star is free to take, and therefore I can just accept E star. Any questions so far?
Sounds good.
Okay. So how do I bound this probability? Well, because I have uniformly random order here, and I have, so the size of the set S is n over E. Sorry, it's floor of n over E. And there are I minus 1 elements in total before step I. Probability that there no element is accepted before I is accepted. This is going to be bigger or equal to n over E divided by I minus 1.
Again, why was it that?
So because the size of the set S is n over E, and as long as, so this is uniformly random order, and I have a set of numbers, as long as their maximum appears in the first n over E, then first n over E elements, then I'm going to have this condition. I have I minus 1 elements in total. So because this is going to be chosen, it's going to choose this place uniformly at random. It's going to be size of S divided by I minus 1.
And if the maximum element appears there, then this is the probability that, no element is accepted before I.
Yeah, exactly. So as long as the maximum of elements before I, so as long as, so if I just look at the elements before I, So I don't care about the ones after that for now. As long as the maximum of them appears in the sample set S, then I'm going to be fine.
Yeah, essentially, if the maximum appears in the first n over e guy, these are the things that we burn it. We don't choose anyone. So if you do
Exactly.
it there, that's essentially, we put the standard high, essentially, and then, so this is the guys essentially appear, we don't select it. And then after that, we don't select anyone, essentially, until we reach I.
Exactly, yes. So now I'm gonna do a slight trick. I'm just gonna ignore the distinction. I mean, you can look at the formal proof later, but like I'm gonna ignore the distinction between like floor and like ceiling and like I minus one, just to kind of simplify the math. And again, like I said, so because all of these values are very like you can think of it as very large, this does not really cause an issue. So. What does this lead me? It leads me that the probability that, like if I sum over all I, probability that E star is accepted is bigger or equal to 1 over n, sum of I equals n over E, n over E divided by I minus 1, right? Which, again, ignoring the distinctions between like, floor and ceiling and stuff, I can like roughly approximate this with 1 over n, sum of I equals n over E, and then this is going to be n over E divided by I. And what I can do, I can just kind of, well, this n gets simplified with this n. I can bring the 1 over E outside. It'll just give me 1 over E, sum of I equals n over E and 1 over I. Now, what is this quantity? This is just going to be, well, this is kind of like, you can always approximate. This is the like sum of 1 over x. You can, sorry, sum of 1 over I over integers. You can approximate this using the harmonic series. So this is going to be approximately log of n divided by n over e, right? Log of n divided by n over e, which is log of e, which is 1. So because of that, probability that E star is chosen, E star is accepted, is going to be bigger or equal to 1 over e. If you don't ignore this,
Just one thing. So here you have assumed that essentially E star appears in position I, correct?
yeah. So yeah. So for any yes. So for position I, if I fix an I, then the probability is going to be like floor of n over e divided by m minus 1. So the quantity here. But then I sum over all of them i's.
And this one essentially here, that was the probability that essentially the maximum of zero. So the maximum of the elements from 1 to I minus 1 essentially it appears in the n over e, correct? So here you will consider like the maximum of these guys, whoever are these guys between, they are those that are in the position 1 to I minus 1. The maximum of them should appear in the first n over e, essentially bears. In that case, no one will be selected because it's because of this maximum, and E star is greater than that. So we will surely select E star at that, correct?
Exactly.
And that's the thing that we have I minus 1 essentially guy, and then the maximum of the first I minus 1 element should appear in n over e position.
Exactly. Yeah. So that should appear there. So that's so as long as E itself appears at E star itself appears at time I, and the maximum of the previous elements appears in the first n over E, then we're always going to accept E star at time I.
Yeah, and as I mentioned, so that is important because we are doing bare. So first, the appears n over e, it means that it is bare and we don't select it. And also it appears there, sets the very max, essentially the high standard that only in this time E star can be accepted. That's essentially both of them together.
Yeah, exactly. Yeah, so this is a proof of the kind of the classical secretary problem. I'm next gonna I'm now going to discuss kind of an interesting extension of this to matching. So this is an algorithm by so I have written the names, but like I'm worried about misspelling them, so I'll just write the acronym. But this is KRTV13. So this is by Kesselheim, Radke, Tunis, and Woking. This is a paper appearing in ESA 2013. And what they do is they have a very nice extension of this to the matching setting, and I'll describe the problem a bit. But yeah, it's a kind of a very nice analysis that yeah, I think you can use the ideas of these analysis to kind of for some different problems as well. And they yeah, so they extend this, generalize this result, and they get 1/e for a more general setting. So what is this setting? I have so think of it by bipartite matching. So the right-hand side is fixed. The vertices on the left-hand side, they're going to arrive in random order. And when a vertex arrives, it's going to reveal the edges that it has connected to the edges on the right-hand side, right? And these are weighted edges. So like, this could have weight 1, this could have 3, this could have 5. But yeah, the vertices on the right are fixed. The left-hand side, they're arriving in a random order. And when a vertex arrives, I have the choice of accepting one of the edges connected to it, right? So if you think of this as kind of like an auction setting, I have, you can think that, I have a bunch of items fixed, right? And the buyers are arriving in random order. And when a buyer arrives, they're going to tell me, I want the, I have valuation 1 for the first item, valuation 3 for the second item, 5 for the third item. Maybe I don't want the fourth item, whatever. They're going to give me all of the valuation lists. And then I can decide whether or not I sell this agent an item, right?
Yeah.
And
so essentially, R here is the set of items,
yes.
L is the set of buyers here, that they are coming one by one. So R is fixed. The people are coming one by one, and these are their valuation. And this is the matching. It means that from each item, we have at most one copies. So if we sell to someone, then we cannot sell to others.
Yeah, exactly.
That's the decision that we need to make.
Yeah, and we also have the concern that we only sell one item per agent. So a buyer will not get 2 items.
Yeah, each buyer and also wants at most one.
So yeah, so for this problem, and like yeah, so I want to design an online algorithm that's does well for this, and like.
And here the goal is to get the expected like the price of those items that we sell, essentially.
Exactly. So
efficiency.
yes, like maximizing social welfare. So I want to maximize expectation of so by algorithm, I'm going to denote, so algorithm here, I mean the matching that is induced by the algorithm. So for instance, if when the first item arrives, I sell item 1, sorry, when the first agent arrives, and when the second agent, so let me just write this with red. So let's say when the first agent arrives, I sell this item. For the second agent, I sell this item. For the third agent, I sell this item. For fourth agent, I don't sell anything. For fifth, I sell this item. Then I'm just going to sum up the number of these edges, and that's going to be the, what I mean here by like the quantity algorithm. I just mean the sum of the weights of the accepted edges. And the goal is to kind of maximize the ratio of this expectation to expectation of the optimum offline matching, right? So regardless of how these items arrive, once all of them have arrived, I can calculate an offline optimum matching on them, and I'm going to kind of try to maximize the ratio between these two.
So we try to maximize the ratio essentially, and note that here is secretary problem is a special case of this. When we have only one item, these buyers are coming essentially in a random order, and each of them essentially has some valuation for this item essentially, and because they are coming in a random order, we want to sell this item to one of these people, and that's essentially the valuation. So this, like the first guy has a valuation 1, the second one maybe have 7, the other one maybe 1,000, and you want to decide only one of these buyers who should get this item. So if the number of items is only 1, this is essentially secretary.
Yeah, exactly. So if I have only a single item, then the matching constraint is just going to be that I can choose one buyer, and basically I can only accept, that edge. So it's just going to be the standard secretary problem. Yeah, so they actually show that you can achieve. Sorry, they show you can achieve so this is referred to as competitive ratio. Ratio. Just CR for short, they can show that you can achieve CR equals 1 over E. So it's very much a generalization of the standard secretary result. Now, how do they do this? The analysis is actually quite interesting. In a way, the math ends up mimicking the same math as the secretary problem. So the way you get 1 over E is still going to be like, you sum over 1 over n times, so if I go back here, if you look at these quantities, I'm still going to end up summing over 1 over n times n over E divided by I minus 1. So in a way, the math is roughly going to match the same thing, but like kind of why you get that math is kind of what I think is more interesting, and it kind of involves a
And
more
notice, I mean,
nuanced
also in the
argument.
secretary, when we had this expectation of opt, so opt was there essentially just E star. And then we get it 1 over E. That was exactly expectation of our algorithm comparing to opt. And we get it 1 E times opt. So that was the same competitive ratio also we had it for secretary.
Yeah, exactly. Yeah. So how do I lower bound the kind of the thing here. So what I'm going to do, I'm going to define alg of I to be the weight of edge accepted at time I. And if there is no wedge, if there's no such edge, I'm just going to set alg of I to be 0. Uh, or 0 if no such edge. Roughly speaking, this is like the contribution of time I to the algorithm, right? And because what is the final set I have? It's going to be basically the sum of it's going to be the union of the edges of accepted at different times. So alg is always going to be obviously sum over all I of, I mean, I can sum from either 1 to 0, like 0 to n, or from, or I can just sum from, oh, sorry, I'm not going to, I haven't mentioned the algorithm yet. Yeah, so this is going to be Algorithmic. Yeah, sorry, I forgot I haven't mentioned the algorithm. Let me mention the algorithm first.
Here by alg, essentially you mean the weight actually. So here, that is
Yeah,
the
by
weight will
algorithm,
be
yeah,
taken out.
yeah, the algorithm, I mean the weight of the edge accepted at time I. So if you think of so if let's say Wi is the weight at time I, then algorithm is Wi times the indicator that Wi is accepted, right? So, or yeah. Or actually, sorry, this is a bit misleading because let me just erase this. Sorry. So because multiple edges are arriving, I can't quite assign that weight to time I, but like yeah, sorry, this got worse. But yeah, by algorithm I mean the weight of the edge accepted at time I, if such an edge exists. Now, what is the algorithm? I forgot to mention the algorithm. So the algorithm is, as before, I'm going to skip the first n over E. Let me see. Algorithm. I'm going to skip the first n over E vertices.
Same as before, essentially.
Yeah, exactly. So, but yeah, so same as before, I'm just going to burn them. Roughly, you can think of this intuition as like, if I just care about constant factors, then, if I want to solve the problem using using all of the elements, well, if I solve it just using the second half of the elements, or like in this case, n over E, sorry, 1 minus 1 over E fraction, then I'm not going to lose that much, right? Because like I'm going to lose at most like a constant factor. But the advantage of like burning these elements is that I gain a lot of information about kind of the elements that I have, and I can use that information to kind of choose the next elements more wisely, right? So as before, I skip the first n over e vertices.
Okay, so
Then at time I, so for
yeah, so essentially to recap, so we can sell at any time just one item, and when one buyer comes, we will see the value to all essentially items that we have.
yes, exactly. So for I is in n over e plus 1 n. So basically after I've skipped the first n over e edges, and sorry, n over e vertices. Then at time I, what I do is I calculate opt of I is optimum matching so far. Sorry, are there any questions? Okay,
No.
so I calculate optimum matching so far. So, up to now, like if I just
So you are essentially ignoring the first n over e. This is what essentially some kind of information gathering in some sense. After that, when it comes, after that, we consider the ice element that are coming. For this I element, including those n over e guys, we compute the maximum matching.
yeah, exactly. So like this, like if I look at like the time step n over e plus 1, for instance, so these vertices have arrived, and so has this vertex now. And so I have like a kind of a partial graph, right? So I haven't seen the entire thing, but I've seen I kind of have part of the graph. I calculate the optimum matching on this partial graph, right? And then let EI be the edge connected to so VI just means the vertex at time I, right? So the buyer that has arrived right now. So I'm just gonna, after I calculate the optimum matching, I'm gonna look at the edge that is connected to this buyer. If there is no such edge, I'm just gonna, ignore. I'm just gonna go to the next buyer. But
So EI be the edge essentially connected to VI, the current buyer.
yeah, exactly. So that's the edge EI. Now I'm gonna try to accept this edge. Now what I mean by try, as if you recall from, previously, there's this condition that I cannot sell an item. I can never sell an item twice. So if if the item that's like so if this edge, for instance, could be end up being like this edge, right? But then it's possible that when when a previous agent arrived, I had already chosen this edge, and this item's gone, right? So in that case, I obviously can't do anything. But let's say if EI can be accepted, then accept. Is this condition?
Compute essentially maximum matching, essentially by this the last guy, including last guy, and see it essentially attached to which item. If that item is available, this is somehow similar to that one. If that we have not selected any item before, that is a similar thing. If you have selected, means that this guy is gone essentially in the secretary problem. So if this guy is available, this item, then we will assign that item essentially to this. Otherwise, we don't do anything.
Exactly. Yeah. So that's the algorithm. And in a way, you can think of this as somewhat similar to the original secretary. So it is a generalization of the original algorithm in the following sense that if I consider just just one item, and I have a set of buyers arriving, what is this basically telling me? It's telling me, calculate the optimal optimal matching. What is the optimal matching going to be? It's going to be just an edge on the maximum weight seen so far, right? So it's going to tell me that, okay, if EI is connected to an edge in the matching, that, when is EI going to be connected? If EI is the maximum so far. It's basically saying that if the element I'm seeing right now is the maximum element I've seen so far, then accept it, right? And this is equivalent to saying that it's the maximum
And of course, if the item is available.
yeah, and of course, yeah, the second condition is it needs to be available. So if it's available and it's the maximum so far, then I accept it. So this is in the special case of like a one item and buyer, this is going to be the standard secretary algorithm. So now I'm going to discuss why this actually gives you 1 over e for the competitive ratio notion I discussed before. And so the proof works like this. So I'm first going to claim that expectation of W of EI is going to be at least 1 over n times opt. So why does this hold? Well, I'm sorry, what is opt? By opt, I mean just the weight of the optimum matching, right? And so this is basically, like intuitively what I'm saying is that, one at a time I'm calculating the optimum matching using the element so far. Then this is going to give me, then if I look at any of these indexes at time I, it's going to roughly get 1 over n times opt, right? So it's kind of saying that the elements are at least spread out uniformly when I kind of...
But by n means the number of elements that arrive so far, correct?
No, no, n is all of the elements. So opt is so this is not opt I. This is opt of the entire opt.
Okay.
Yeah. So how do I say this? Well, first I claim that expectation of W of EI is bigger than 1 over I times opt of I, or like, let's say expectation of opt of I. Intuitively, why is this? Like if you fix the first I vertices, right? So if I first fix the set of first I vertices, I don't fix their order yet, I just fix their set. Then I'm going to have the set opt of I, right? Then these first I vertices are going to be uniformly at random, right? So because of that, when I look at the optimum matching, right? So if I fix a set of I vertices, I'm going to have a matching that's going to have, size opt I, and yeah, so because I'm spreading these, because these elements are arriving uniformly at random, each of the time steps is going to have expectation of W of EI is bigger than 1 over I of that opt of I. So look at like, alternatively, you can just say that expectation of W of E1 plus, oh, sorry. I don't want to E1 because that would be misleading.
What was WEI? WEI was the alg things?
Yeah, W of E, so EI is the edge accepted connected to VI in
Yeah.
the optimal matching at time I.
Or at time I. Okay. Yeah.
But EI is not necessarily accepted. So I'm not discussing whether or not it's accepted yet. I'm just claiming that its weight, even if it's rejected, I'm just going to claim that its weight is at least 1 over n of opt.
So WI essentially, like if there is an EI, which if EI essentially matched or not, it would be 0, then there would be some edge that is connected to that in the matching.
Yeah,
WI is the weight of that edge. And like we don't know whether it is available, like whether we can assign it yet or not. We just talk about the weight of it.
Yeah, so this way is going to be 1 over I expectation of opt I. What is the reason for this? Is because, because the elements are arriving uniformly at random. If I fix that set, like each of the vertices, like the edge connected to it in this optimum matching, these numbers are basically going to sum to opt I. And because I'm like picking one at random and putting that to be the element at time I, this inequality holds. So this is the first claim.
What is opt I?
Opt I is the optimum matching calculated at time I. So here at time I, like I was between n over e and n, I calculated the optimum matching using whatever I've seen so far.
And again, so can you explain why again this W of EI is greater than 1 over?
Yeah, so if you look at, so let's say I fix the set of the vertices 1 to I. I don't fix their order yet, I just calculate their set,
Yeah.
right? So I'm going to have something like a matching like this. Oh. Why is it not writing? Okay. I'm going to have a matching like this. So this is not all of the elements. This is just the first I elements.
Yeah.
Right? Oh, sorry. It can be a magic, right? So let's say this is connected to this. Let's say this last one's not, yeah, let's say this one's not connected to anything. And this one is connected to this, right?
Yeah.
And let's say this is 1, this is 3, this is 2, this is 5, for instance, right?
Yeah.
So I fixed these vertices. Now, what happens if I'm next going to fix the decide which one of these vertices is going to be vertex I, right?
Yeah.
So if this first one is going to be vertex I, then EI will be EI is going to equal 1, right?
Yeah.
Because the kind of the main point here is that the value of the optimum of the first I vertices is irrelevant of their arrival order, right? So regardless of their arrival order, I can calculate this optimum matching. I can then decide which of them is going to arrive at time I. If this first one arrives, then EI is going to be 1. If the second one arrives, EI is going to be 3. Third one arrives, EI is going to be 2. Fourth one, EI is going to be, sorry, this is like some AI features I thought I managed to turn off, but yeah, is equals EI equals 2. Fourth one, EI is 0.
And so, what is the difference between matching at time I and matching at time I minus 1? Are you using any properties of that here?
Not yet. No, I'm just yeah. So I'm not using any properties of that. No. Yeah.
Okay. So that is like you are talking about just 1 over I of E of opt I essentially. Okay. So far you didn't use anything. Yeah.
Yeah. So because of that, because the edge vertex that arrives at time I is going to be chosen uniformly at random from this like the set of first I vertices, expectation of WEI is going to be 1 over I expectation of opt I. Now the second
Opt I is the optimum at time I.
Exactly, yes. The second claim is that expectation of opt I is going to be bigger than I over n expectation of opt. So this is saying that the optimum matching at time I has roughly I over n, expectation of opt. Intuitively, this kind of makes sense. Like if the first half of the vertices have arrived, I kind of expect to, and because it's uniformly random, I kind of expect them to have half of the weight of the optimum matching. Why does this hold? This holds because well, you can always lower bound. It's like instead of opt I, consider the set define set AI to be, or like let's say I might use a different letter. Define set E, let's say xi, to be, let's call it the restriction of opt to first of opt to first I vertices.
Yeah. I mean, the first I this is essentially opt as assigned something that we know that is less than opt of I essentially.
Yeah, exactly. So this is when I say restriction of opt, this is the actual opt, so the offline opt. So the algorithm wouldn't know this. This is just for the purpose of analysis. But like once all of the vertices arrive, I can calculate the entire opt, right? And then I'm gonna look. Okay, so the entire opt is gonna be something like, it's gonna assign this vertex to this. It's gonna assign this vertex to this, or it's gonna assign this vertex to this, right? And let's say I is 2, so I only care about the first 2 vertices. Right? So the restriction is just going to be these 2 vertices, right?
Yeah.
Sorry, these 2 edges. Now, this restriction is always going to be, so the claim is that expectation of xi, and when I say expectation of xi, I mean the sum of the values in xi, because xi is technically a set, but like expectation of the sum of the values in xi is going to be bigger or equal to I over n expectation of opt. Why does this hold? This is because if I take any of the vertices, if I take any of the edges in the actual opt, it has probably I over n of appearing in the set xi, right? Because as long as that vertex arrives in the time steps 1 to I, then it's going to appear in xi, right? And the probability of that occurring is I over n.
Sorry, can you repeat this one?
So what is expectation of xi? This is expectation of like the sum of this restriction, right? What is this restriction? I'm just looking at all of the edges from the entire opt that appeared in time I between time steps 1 and I, right? So what is the expectation going to be? It's going to be, it's going to be sum over, I can kind of write it like this, right? This is going to be sum over W of sum over E is an opt, W of E, probability that E appears at time steps, between 1 and I.
Yes.
This is going to be, and this probability is going to be bigger than I over N. So this is going to be bigger than I over N, sum of W of E. This is just going to be N E is over opt. This is going to be basically I over N times opt, right? So this restriction, restriction xi is going to be at least, is always going to be at least I over N times opt. But I also know that this restriction is always a matching, right? Because if I have any matching and I take a subset of that, then it's always going to give me a matching as well. It's like a downward
Because of
slope.
that should be less than expectation of opti.
Yeah, and it's always less than or equal to expectation of up I, because like by definition, expectation of up I is the optimum matching at time I. Yeah. So yeah, because of those two, I have this property. I'm gonna use more colors. I guess I'm gonna have this crucial I don't know, it's gonna be dark. I have this crucial inequality here. And this is kind of roughly saying, if you recall the previous analysis we had for the original secretary, what were we saying? We were saying that I had this quantity 1 over n of the probability of the element E star arriving at time I. This is kind of serving a similar role. Before I was saying that, okay, with probably, if I look at time I, what is the probability that E star appears there? It's clear that it's going to be 1 over n. Here, I'm asking a similar question. I'm asking how much can the element at time I possibly contribute, like if it is accepted. So I'm not going to discuss whether or not it can actually be accepted yet, but if it is accepted, how much can it contribute? Then I'm claiming that it's going to be opt over n in general. So it's kind of a, the argument was slightly more involved, but kind of the end result is like the math ends up being kind of similar. It's like before it was 1 over n, now it's opt over n. But like it was 1 over n before because like I was just looking at probabilities. So if I looked at weights, it would actually be the exact same thing. So that's the first claim. And notice that for calculating this, for like expectation of WI, the only thing I need to do, the only thing I need to actually like realize is the edge EI itself, or like, I don't need to actually realize all of the arrival order. This is kind of a subtle point, but it's an important point in terms of the analysis. Before, we were looking at the arrival steps, kind of the arrival order in like 1 or 2 steps. Now we're actually going to look at it in a more nuanced way, in like a step-by-step manner. So the next claim I have is that probability that EI is free to accept. And what do I mean by this? I mean, like, look at the edge EI, look at the item, it's, look at the...
Sorry, just one thing. Did we use the E of opt I is greater than 1 over n E of opt?
E of opt I is...
Did we use that things? I think we have used that one, correct?
For which one? Sorry.
This E of opt I is greater than or equal to, okay, from this 1 and 2, essentially you got that.
Yeah, exactly. So this claim, so let's call this, I don't know, like lemma 1. Lemma 1 follows from claim 1 and claim 2.
Yeah.
Okay. So I'm not going to discuss the, so probability that EI is free to accept. I'm going to claim that this is bigger than equal to n over E divided by, n over E divided by I minus 1, right? So the same quantity as before. But the argument now is going to be slightly more nuanced. So what was the
After
argument?
that, I mean, we are done essentially.
Yeah, then the exact same math is going to go through. Like the only difference is that like I have a factor of opt here, but then it's going to be, once I show that, then expectation of alg is going to be like lower bounded by like opt times 1 over n, sum of I equals n over E till n of n over E divided by I minus 1. As before, I know this is going to be like roughly 1 over E. So I'm going to get, in total, I'm going to get, for the whole thing, I'm going to get opt divided by E. So I just need to show this inequality, which I'm going to call lemma 2. Yeah, so why does this hold? I forgot okay. So this is kind of a nuanced argument, but yeah, I think it's actually a nice part of the result. So how was I arguing about this before? Before I was saying that, look at the first I items, and then look at the maximum element here. And then if, sorry, not S. And let's say the first N over E is going to be here. I was saying that as long as the maximum element appears here, then I'm going to be fine, right? So that was the argument. In that case, then, what is the probability of that? That's N over I minus 1. Here, I can't quite make the same argument, but what I can do instead is I can kind of start going back in time and calculate the probability of the element becoming unavailable at any of the previous time steps. And I can this will give me like a product that'll end up kind of giving me the same quantity of N over I minus 1. So what I mean by this, so what does it mean for so what does it mean for EI to be not free to accept? So EI is not free to accept. To accept means that if I fix, so because I fix EI, think of EI as a vertex VI connected to some item U, right? This means that U is already taken, right? So all I need to do is I need to lower bound the probability. I need to show the probability that U is taken by time I is less than equal to 1 minus N over E divided by I minus 1. This is all I need to show. But what is this probability? Well, how can U be taken by time I? Let's fix all of the vertices between 1 to I, not their order, just the first I minus 1, right? And let's then start realizing the order in reverse. So I'm first going to take one of these vertices in random, and I'm going to set that to be Vi minus 1. I'm then going to continue and take another one and set that to be Vi minus 2, and then take another one and set that to be Vi minus 3. I'm going to continue all of this until I get to V1, right? Now, when I choose a vertex Vi minus 1, so at this initial stage, the set of vertices V1 to Vi minus 1 is fixed, not their order, but their set is fixed. So because of this, the set opt I minus 1 can be calculated, right? And this will allow me to calculate that EI minus 1, right? And as long as EI minus 1 is not connected to U, then U will not be taken at time I, right? So if you recall the algorithm, it only accepted an edge if it was the only edge it could possibly accept at time I was the edge EI. So the edge that was connected to the vertex VI in the optimum seen so far. So as long as the edge EI minus 1 is not connected to U, then I'm going to be safe for this time step. So U is not going to be taken in this time step. Now, what is the probability that EI minus 1 is not connected to U? I claim this is bigger than 1 minus 1 over I. Why is this? Because when you look at time step I, sorry, 1 minus 1 over I minus 1. So when I look at time step I minus 1, all of these vertices have arrived. the set up I minus 1 is going to be fixed, right? So I haven't realized the order yet, but that set is fixed. Now, what does this set look like? It's going to be a matching. So there's going to be at most one edge connected to the vertex u, right? So one of the, yeah, so at most one edge connected to the vertex u. That means there's only one vertex. So let's call that vertex, I don't know, v prime. Then as long as v prime does not arrive, at time minus one, then this is basically going to hold. So the only way I can be in a bad situation is that v prime is exactly the vertex that arrives at time I minus one. But what is the probability of this happening? This is going to be at most 1 over I minus 1, right? Or you can think of it as an equality. For now, let's assume it's an equality. There's a subtle point for which it's not an equality, which is that such an edge might not exist. But it's clear that this probability is at most 1 over I minus 1. Is this clear, or are there any questions?
No, I think that seems fine.
Okay. So this is the probability that EI is, EI is not connected. EI minus 1 is not connected to U. So, and again, for this probability, all I need to do is realize the randomness of the vertex VI minus 1. I did not yet need to realize the previous order of the previous edges. So I continue this. So this is with this probability, I'm going to be fine for this time step. Then what is the probability that EI minus 2 is not connected? Then this is going to be bigger than 1 over I minus 2 for the kind of 1 over I minus 2 for the exact same reason, because I have I minus 2 vertices now, and only one of them is going to be possibly connected to U, right? In the optimum matching. And as long as that is not the vertex that arrives, I'm going to be fine. Sorry, I need to quickly bring my charger. It was full charge. I thought it would last. I'll be right back. Probably that EI minus 2 is not connected to U. And I can kind of keep this math going to probability that like E n over E is not connected to U. Is bigger or equal to 1 over 1 n over E, right? And I actually don't need to go past this point because I know that there's no way that, yeah, so as long as B
The other one you have not selected.
Yeah, the first n over E vertices are not selected at all, so I don't really need to consider them. So what happens when I, multiply these numbers together? Well, the first one's I minus 1, sorry, the first one's I minus 2 times I minus 1, right? So this equals I minus 2, I minus 1. This equals I minus 3, I minus 2, I minus 3 times I minus 2. I can keep this math going until I get n over E minus 1 divided by n over E. And all of these numbers are now going to cancel out. And I'm going to be left with floor of n over E, because ceilings minus 1 is going to be floor, divided by I minus 1, right? So this is what I'm left with. And if you recall, this is the same quantity as, or sorry, there's no reason for minus 1 here. So there was a ceiling and there's a floor. Yeah, so this is the same quantity as what I was looking for here, right? Same quantity. So yeah, so the argument of like why we get this quantity is very slightly more involved than the argument we had for.
Can I see these telescopic multiplications?
Yes, sure.
Do you just multiply essentially this?
Yeah, I multiply. So the argument is slightly more involved. In the previous case for standard secretary, we were just saying, we can just look at the time. We can like look at whether or not the maximum arrives at the first the burnt element. The argument's kind of more involved here. I'm like looking at each time individually. You can check
and
if
then
you
you will
want
multiply because essentially none of these events should have happened because none of them should have been connected to you.
Yeah,
So
exactly.
that would be the multiplication. That would be a 6.
Yeah, and like I can assume an independence argument because like it's like conditional independence basically because the way in which I'm realizing the random variable is important, right? So it's like in order to like obtain my permutation of the elements, I first pick I first randomly draw the edge or let's say the vertex I minus 1 from the remaining vertices. I then, randomly draw the I minus 2 and kind of keep going back. So this is equivalent of a random permutation, but this, element by element view allows me to kind of look at the, calculate each of these probabilities individually. You can actually check that the same proof would also work for standard secretary. That would be other like kind of more involved way of getting the same bound, but like yeah. So for here we do need this more involved proof.
So here, note that the secretary we wanted to select essentially so in the secretary we wanted to just select one item essentially. Here the goal is to select actually more than one item, and it's the matching. Now, this is like the important thing. There are two important combinatorial structures. One is the matching, essentially. The other one is the matroid as well. And I think that is the question is that now these K guys that you are selecting, in some sense here you want to have a form of matching. There you want to form essentially matroid. So that's the same thing that we can just talk about some of the things that this strong matroid secretary, whether essentially if you want to do this selection K of these guys, in the matroid setting, whether this 1 over E we can get it or not. That is called a strong matroid secretary conjecture. And so far, the best upper bound is only log the base of the matroid, so that Kiarash can talk a little bit more about it. But the strong one is that you should get the same thing that you get it for matching. Generally, the thing that we can get it for matching, for example, for profit matching and profit matroid, we can get essentially the same numbers. Here, somehow the conjecture is that yes, for profit matroid also we can get that one for matroid secretary. But just the weaker version or this one is that can we at least get a constant? We don't know that. The only thing that we know is like N or like K, essentially K the base of the matroid. So we don't know anything close to constant. Yeah, Kiarash, do you want to just say a little bit more about
this? Sure. And like one important point that I think is kind of interesting, and like this is why intuitively why this analysis, even though with more math, is getting carried over. If I look at the element EI, like in order for it to be free, I just need to look at a single vertex U and I need to ensure that that U is free. It's like there's only one way in which the algorithm can like end up blocking EI, and that's by accepting U. Or you can think of it as like because only one edge is accepted per time step. The probability of like that element being blocked at time I is not that high, right? So all of these math goes through. For matroid, you can't quite make this argument. So I can so do you want me like Mohammad, do you want me to like recap the state of the art for matroids or like the
yes, that would be good. So I think we talk about the matroid essentially. So in general, the matroid is something that it is come from linear algebra type of thing. You have a set of vectors and you will consider base of them. Base essentially in an independence, that means that the set of vectors are essentially independent. And just the base means the maximally size independence. So we can say that all of them have the same size. It is called the rank of the matroid. There are lots of special cases of the matroid. This linear one is essentially one of the most general form. So, and we have this one, we all have the ranks are the same. And we know that if on the bases, these are the maximal independence set. And we know that all of them have the same size. And if one essentially set is independent set, all of the subsets also independent. So this is something called downward monotonicity that we talk also for profit profit inequality. So we have this downward monotonicity, and of course we have one more condition that if we have two sets and one independent set has larger than the other independent set, from the bigger one we can put one essentially always there is one element in the bigger one that we can add it to the smaller one and still it is independent. These are essentially the property of matroid, and it has lots of things, especially this kind of independence. You can think about like in the auction type of things that you have a set of, for example, a set of people you want to select such that each of them have some kind of unique aspect, for example, that like you want to select some set of news, for example, in LLM to use all of them to give better response. You want to make sure that these are somehow not repetitive. Repetitive means they are essentially independent. So there are lots of essentially applications for that. And yeah, Kiarash, you can go.
Yeah. So so the matrix is like kind of they're Okay. Let me sorry, I don't know if the quite function. Okay, maybe it's like I can just make a new yeah. So there so yeah, so the matroid I mean the formal definitions are kind of not very clean. They're like two properties of Mohammad mentioned. So it's like the downward closed the downward monotonicity property, where like you can, if A is independent, any subset of it is independent. The other one is this exchange property. But like there, like one reason you can immediately kind of become this, another reason like why metrics are important is like the special cases it has. So like one special case would be the K uniform matroid. So basically, I have a set, larger set E, all subsets. You know, and E has an elements, and I have some value K, which is, let's say, much smaller than N, like K is like, I don't know, like 10 or something, like 10. All subsets of size at most K are the independent sets. So that's one immediate special case. Another special case is the graphic matroid. So the graphic matroid is the elements of the matrix are going to be edges in a graph, and a set is going to be independent if it does not have any cycles. So as long as it's like a forest, it'll be independent. But if the set has a if it has a cycle, then it will not be independent. So this is kind of another important matroid. Another important matroid is like the linear matroid. So this is, yeah, as Mohammad mentioned, this comes from linear algebra. Just think of a bunch of vectors in the in some field, like real valued, whatever, in some vector space. Then I'm going to call a subset of these vectors independent if they, you know, if they're like linearly independent, right? So if one of them is spanned by the other ones, then, you know, I'm not going to call it independent. Or like if the determinant is zero, you know, lots of different ways of checking the condition. But otherwise, if all of the vectors are independent, then I'm going to call, you know, the matroid, the elements in the matroid to be independent. And so for, yeah, so a key question is like, what is the best competitive ratio we can get for the matroid secretary? So like I have some matroid, its elements are going to arrive in random order. Each of them is going to have weight. I want to maximize the expected weight of the accepted set. So there are also some other examples which I'll just mention because they're kind of interesting. One of them is like transversal matroid. The other one's going to be laminar. These are all important special cases, and for all of these, you can actually not this one, but like for all of them except for linear matroid. But for these ones and some a bunch of other special cases of matroids, you can get constant factor competitive ratios. But yeah, so for linear matroids and like some other matroids, but like for instance gamoids, you cannot like it is not known whether or not you can do this. And yeah, a key open question is basically the matroid secretary conjecture, which says that you can get constant for all matroids, right? You can get constant. Right now, the best result we know is log k, and this is due to
And K is the essentially rank of the matroid, which is the size of the maximum independence or the base.
K is the size of that. Yeah, exactly. Yeah. So this is a result by Feldman, Svensson, and the conclusion. Sorry, this is the. I mean, these are kind of two independent. There's another one. Sorry, one second. Sorry. So this is a simpler. So this implies so there's a previous result. I forgot the yeah. So this is a paper in sort of 2014, but so this is I won't go through the proof right now, but this is like a if you want to like read a short proof of this, this is where you can find it. The original result was by sorry, Oded Latish. This is I think Fox 2014. I think this is Fox 2014. Yeah.
Can you write it down?
Yeah, it's I think it's Fox 2014. double check. Yeah, this is Fox 21st. Yeah.
Sorry, where did you write?
Oh, I think there was an issue with the screen share. Sorry. Because I checked something on the laptop. Let me stop sharing and reshare. It should be good now, right? Yeah. Can you see the screen now?
Yes, but
Yeah.
also say that the first one was the Soda 2000.
Yeah, I mean, technically this was this is where the result first appeared, and this is another kind of an alternative, simpler proof. I'm really mentioning this because, like, if you want to go through the proof, this is much kind of much more accessible, I guess. Yeah. It's using a simpler algorithm, but yeah, these all get like O of log k for the problem. And it's also log k. So first, yeah, the original problem paper that introduced metric secretary, they introduced, I think, an algorithm with a log k competitive ratio. This was then improved to square root of log k, and later improved to log k, and this is kind of the state of the art right now. This is for, yeah, it hasn't been approved since 2014. So this will be the matrix secretary conjecture. Strong matrix secretary says that you can get this, you can not just get a constant, but you can get 1 over e. So matrix secretary just conjecture itself just saying that you can get constant, but strong would be that you can get 1 over e. And like we don't know 1 over e for all of these special cases. So for this, actually, we do know 1 over e. So this is fine for graphic. The best known bound is like I think it's actually our paper. It's like 3.95. The linear matroid, yeah, whether or not you can get
Hey,
constant
you
is
mean
open.
1 over 395?
Oh yeah, so if you want to divide, yeah, depends on which way you're, yeah. For transfer cell, you can get 1 over e. Laminar, I don't remember the exact numbers, like 0.3. 1 or something. I don't remember the exact number, but like it's close. It's more than it's like more than 0.3.
What was essentially for graphical matroid in terms of the reverse 0 point?
It's like slightly higher than it's like 0.26 something. I think. But yeah, I can calculate that. But yeah, so these are kind of the special cases that are known, but yeah, so whether you can get 1 over e for all of these, for all of these that, it's not known whether you can 1 over e, that's obviously an interesting, important question. In general, a key question is where you can get 1 over e for everything, or even constant for everything. These are all kind of important questions that remain in the area. And like, I should say, an interesting thing is that the algorithm, so the algorithm I mentioned by, so KRTB13 paper, the matching one. The ideas from those algorithms, you can actually use it for a lot of the settings. You can use it, for instance, in the graphic matroid setting. You can use it for K-uniform matroid. Transversal matroid, actually, that was the first paper that got 1 over E. You can kind of, the matroid definition is actually closely related to matching. So you can immediately use that matching algorithm to get a 1 over E for this. For laminar even, I mean, the best known is also kind of using similar ideas in terms of the analysis. But yeah, I mean, you generally cannot directly apply the same algorithm, though you do need some changes. Like for instance, for graphical matroids, if you want to get 1 over 4, which is like already pretty decent, it's kind of close to the optimum, close to the best known so far, then you can actually kind of reduce the problem, like intuitively you're reducing the graphic matroid problem to picking a good matching in some auxiliary graph. And because in that auxiliary graph, you can get you can kind of use a similar analysis to show the 1 over 4 bound.
Yeah, so as I mentioned, so this is like, as I mentioned, for profit setting that we talked, like matroid and matching are two important combinatorial algorithms. Especially maybe like there is something like they reach to the concept of matroid matching, or matching matroids. Actually, that is the one that combines both of them. But otherwise, these are two independent things. For profit, we can get both of them half, and it is tight. Essentially, the wrong version of matrix secretary is that it should be the case also for secretary, but so far we are very far from proving this. For some of these, we can get just some constant, but especially for linear or gamoid, we don't know constant, of course, for general cases.
Yeah, and like one intuitive reason, by the way, like why you cannot immediately. So the previous algorithm of like previous algorithm that I mentioned for the matching, like that, what does it do at each time? It's like calculating the optimum and looks at that element, tries to accept that. Like that's a general high level idea you can use for all of these matroids. But you cannot use it immediately. You do need to like make some restrictions in the matroid because you do not have the property that you had with matching, which is like only a single vertex can block you. So previously, because only a single vertex can block you in the analysis, the probability of, as long as you don't accept that vertex, the probability of that's also gonna, is gonna be like decently, it's gonna be like some, you can lower bound that with some constant, right? So as long as you don't accept that vertex, then you can accept the current vertex. In matroids, however, this does not hold. So one important example is like the hat example. So this is a famous example that's kind of the basis of a lot of counterexamples for greedy-like algorithms for matroids. Basically, in this example, you have one huge vertex. So actually, let me show this with the different.
Like in the graphical matroid, that essentially you don't want to have a cycle. You want to have a set of edges that they don't have a cycle, essentially.
Yeah, so I have this huge huge edge. Like this has
like
a
huge weight, you mean?
Yeah, let's think of this as the weight of infinity, right? And I also have a whole bunch of edges that are like this. So it's like these, my vertices are going to be like these two vertices, plus a whole bunch of vertices like this. And the weight here is infinity. Think of all of these weights as like 2 plus or minus epsilon. So like slightly, like let's just perturb the weights so that, none of them are equal, but like roughly all of them are 2. All of the edges here that are like above, in the, above part of the graph. Here, all of the edges have weight 1. Then, if you think of like a greedy like algorithms, which what they do is they try to like accept an edge as long as it's in set opt. Then these all of these algorithms kind of fail in this example. And like intuitively, the reason is there's a lot of ways in which you can span this infinity edge. So like previously in the matching, like I said, the only way in which you can block an element is if like that vertex U was taken. And that's, there's not many ways you can do that, right? There's only a single edge at a per time step. But here, intuitively, there's like much more ways you can block the element. And if you use the standard greedy algorithm here, what's going to happen is that with high probability, you're going to accept, so with high probability, before you see the, infinity edge, you're going to see one of these vertices, you're going to accept one of these vertices that are below, and you're going to accept because this, sorry, one of these edges. So one of these edges that are in the bottom, you're going to accept it because that's in the optimum. Once you accept that, if later this edge that is like weight 2 and is in the upper part of the graph, if that arrives, you're going to accept that as well, because that's also going to be in the optimum. Once you accept that, then you're not going to be able to accept this infinity edge, right? So this is going to be blocked, and you can't accept that. So this is kind of a famous example. It's kind of the basis of a lot of counterexamples for instance, why greedy doesn't work.
No,
You
it
can
is
think of
called hat
variations of
example.
greedy, and they wouldn't work as well. Sorry, what?
It is the hat example. It's like essentially
Yeah.
counterexample for lots of other algorithms that the people try to get constant. They are getting from these things. As Kiarash mentioned, this infinity essentially can be blocked with lots of things. Essentially, like as soon as you are selecting something, like one of these 1, 2, then you cannot select infinity because then you have a cycle, and you should not have a cycle in graphical matrix. And that's essentially the problem that. Like we cannot just relate it with one vertex with it is not covered. We can select it as U things. There is no U things. There are lots of these guys essentially that they work together. Anyhow, so I think that sounds good. And this is, as I mentioned, this strong one essentially refuting that strong one or proving essentially the regular one, the matrix secretary that has a constant. It's a very big open problems in the field. And I think we are done for this part. I think we covered almost all important things here for secretary problem, which comes lots of online actions out of it. And I think, yeah, we can just...
the recording stop or?
No, it is there.
Okay.
So,
oh,
yeah, so
okay.
we have everything. And essentially, I mean, thanks, Kiarash, for the presentation here. And we had discussion. So we have finished essentially the secretary, and we already finished prophet, delegates, and other stuff. Okay, thanks everyone, and then bye.
Bye.